So let us now take a look at how to solve for this minimum variance portfolios analytically. So this is what is known as the Markowitz problem. And we are going to frame the minimum variance portfolio problem as a mathematical problem whose solution will lead us to the portfolios that we are interested in. So first, let us write the setup in the correct notation. So as usual, we have got n assets, and the mean rates of return for these different assets are given by R1 bar, R2 bar, and so on, and the covariances are given by sigma ij. Portfolio is defined by a set of weights such that the weights sum up to 1. So this is standard what we have been discussing. So let us now, using this notation, think about what do we mean by minimum variance portfolios. So it has actually got three components. So let's think about it one by one. So what we want to do is that we want to select an arbitrary constant, right? And for that constant, we want to create a portfolio whose mean rate of return is going to be equal to that constant. Okay. So we want this portfolio to be feasible, which means that we want the sum of the weights to be equal to 1. And among all such feasible portfolios whose main rate of return is equal to this arbitrary value R bar, we want to select that portfolio which has the minimum variance, right? So that's the idea. So let's see how in this mathematical formulation, we actually kind of like have all of these criteria. So first, we want to select a feasible portfolio. So that gives us that the summation Wi equal to 1 has to be one of the constraints in our optimization problem. Secondly, we want the mean of this portfolio, the mean rate of return for this portfolio, to be equal to R bar. So this is where we get this second constraint. And among all such portfolios which meet these two conditions, what we want to do is identify the one which has the lowest variance. So if you see the objective function, it says minimum of half of this expression. And you can recognize that this expression is nothing but the variance of the portfolio, right? Now, why do we have a half? Well, you'll see that it will just help us to actually do some calculations in a much more convenient manner. And adding or rather multiplying by a constant does not really change any problem, right? So if you were multiplying fx and if you were multiplying a constant times fx, right, we are minimizing both of these functions, this will lead to the same outcome, right? So this is basic calculus. Okay. So now that we understand the mathematical problem, let us look at how to solve this. So this is a constraint optimization problem, and we can use the Lagrangian method that we have discussed before, right? So recall that in the Lagrangian method, we first write the objective function, which is this expression that you see on top. So that's the first term. And then we rewrite the constraints in a way so that they are equal to 0, right? So this, for example, summation Wi Ri bar minus R bar, okay? And we will multiply that by a Lagrange multiplier. And similarly, we have another constraint, summation Wi equal to 1. So we can rewrite that as minus mu times summation Wi minus 1, right? So this is standard what we have discussed so far. Okay. Now, what we need to do is, in order to solve this problem, we need to differentiate the Lagrangian with respect to the choice variables, okay, and set each of these derivatives equal to 0. Now, what are the choice variables? Well, if you look at this problem, the choice variable is basically nothing but the weights, right? Remember, what we want to do is we want to choose a portfolio, and a portfolio is nothing but a set of weights, right, which satisfy this condition. So therefore, our choice variable here is Wi, where I takes the value 1 to n. Okay. Before we solve it more generally, let's just first try out to simplify the problem by looking at what happens when you have got n equal to 2. So we are rewriting this expression that we have when we have n equal to 2 just to get our idea fixed about, how are these first order conditions going to look at. In case you are very comfortable with these notations, you can go ahead and write down the first order conditions for this general problem. But oftentimes, what we have found is that in our experience, we are better off trying to first solve a simpler problem and then from there understand how to generalize. So we are trying to write down the Lagrangian for the special case where n equal to 2. And if we do that, then the objective function becomes W1 square sigma 1 square plus 2W1 W2 sigma 1 2 plus W2 square sigma 2 square. The first constraint that you have, summation Wi Ri bar minus R bar, So that is nothing but W1 R1 bar plus W2 R2 bar minus R bar. And then again, you have also this constraint that W1 plus W2 minus 1 has to be equal to 0, right? So that is this aspect of the Lagrangian that we have written down. Now, we want to take the derivative with respect to W1 and set it equal to 0. So if we do that, we end up getting sigma 1 square W1 plus sigma 1 2 W2 minus lambda R1 bar minus mu equal to 0. And if we take the derivative with respect to W2 and set it equal to 0, we end up getting sigma 2 square W2 plus sigma 1 2 W1 minus lambda R2 bar minus mu equal to 0, right? So for n equal to 2, what happens is that you have got these two equations and you have got also the two constraints W1 R1 bar plus W2 R2 bar is equal to R bar and W1 plus W2 equal to 1. So you have got in all 4 linear equations in 4 unknowns, right? So the unknowns are W1, W2, and the two Lagrange multipliers mu and R. So this is a pretty straightforward problem to solve. But more importantly, it also tells us how these first order conditions would look like when we look at the general n case, right? So we note down the results here. You can also derive it using the similar methods as we have just discussed. So the n portfolio weights, Wi, and the Lagrange multipliers lambda and mu that we have for an efficient portfolio. And here we are going to allow for short selling. We'll discuss later on what happens if you do not allow for short selling. So that will lead to additional constraints being imposed. Having mean return R bar, which here for us is a parameter, needs to satisfy these n plus 2 equations. Okay. So the first order conditions are going to look like summation I from 1 to n sigma ij wj minus lambda ri bar minus mu equal to 0. And this has to be true for all values of I from 1 to n. Okay. And then you have the two constraints as before. So let's just make sure that this is exactly what we had for the n equal to 2 case. So let's first do for I equal to 1. So this is saying that from 1 to 2, you are going to have sigma ij. So sigma 1, 1, W1. Sigma 1, 1 is nothing but sigma 1 squared. That's the first term. Plus sigma 1, 2, W2. That is the second term that you see. Minus lambda R1 bar minus mu, right? Again, this is what you see, right? And the second term is going to be sigma 1, 2, W1, or rather sigma 2, 1, W1, which is the same thing, plus sigma 2, 2, W2. So again, sigma 2, 2, W2 is sigma 2 squared W2 minus lambda R bar 2 minus mu equal to 0, right? So we can see here that this is consistent with what we had found. Okay, so again, this is not a very complicated object to solve because these are all linear equations in our unknowns. And we have got n plus 2 equations in n plus 2 unknowns. And as long as these equations are consistent, you can actually solve them, right? So let's look at a particular example to see how all of this works out. So suppose that you have got 3 uncorrelated assets, and each of these assets has variance 1. And the mean values of the rates of return are given by 0.1, 0.2, and 0.3 respectively. Now, if you rewrite these first order conditions here for this 3 asset problem, you end up that the first equation is from here, W1 minus lambda R bar 1 minus mu equal to 0. Now, let's think about why the first equation is just W1. Well, you have got sigma 1, 1, W1. So sigma 1, 1 is nothing but sigma 1 square, and you are given that the variance is 1. Hence, the first term is W1. And then you have got sigma 1, 2, W2, but sigma 1, 2 is equal to 0. How do we know that? Because these assets are uncorrelated, right? And similarly, sigma 1, 3 is equal to 0 as well. And hence, that does not enter this first equation as well. And then you have got minus lambda times R bar 1. R bar 1 is equal to 0.1. And hence, you end up getting 0.1 times lambda. And finally, you get a minus mu here, which is this term, right? Similarly, you can go through these exercises. You end up getting the second equation as W2 minus 0.2 lambda minus mu. Again, why do we have W2? Same reason as here, because the variance sigma 2 squared is 1 and sigma 1, 3, sigma 2, 3 and sigma 1, 2 are equal to 0, right? So that's why only this whole term becomes just W2. And then from here, you have got minus lambda R bar 2 and R bar 2 is 0.2 minus mu, right? So that's how you get the second equation, and the third equation follows similarly. How do we get this fourth equation? So remember that summation wi r bar I has to be equal to r bar. So here we ended up getting basically 0.1 W1 plus 0.2 W2 plus 0.3 W3 is equal to r bar. And we just to avoid the decimal points, we have multiplied throughout by 10 in order to get this equation. And finally, the third equation is coming from the, as usual, the sum of the weights must add up to 1. So again, you end up with these 5 equations in the 5 unknowns, W1, W2, W3, lambda, and mu. And this is pretty, again, straightforward to solve. What we care about are these optimal weights. And so we end up getting that W1 is equal to 4 by 3 minus 5 R bar. W2 is equal to 1 by 3, and W3 is equal to 5 R bar minus 2 by 3. So the standard deviation at the solution is given by square root of W1 square plus W2 square plus W3 square. How do we see that? Remember that the standard deviation that we had was summation over I from j equal to 1 to n wi wj sigma ij. So anything that has wi wj where I is not equal to j, so the sigma ij is equal to 0. So the only thing that survives from here is that when you have got j equal to I, right? And in that case, we have got the wi square, and you are multiplying that by the variance, which is equal to 1, right? Hence, this is the W1 square plus W2 square plus W3 square is the variance, and then therefore the standard deviation is the square root of that. So if you now put in these values of W1, W2, W3, you will end up getting 7 by 3 minus 20 R bar plus 50 R bar squared, right? So what is this telling us? So this tells us that for the given value of R bar, what's the lowest value of sigma that we can achieve, right? So now if you go back and think about it, this is nothing but this minimum variance set that we have discussed, right? And we can also find out what's the global mean variance. So how will we get that? So what we want to think about is what's the smallest value of sigma on this line. So that will happen when this is minimized, and this will be minimized if you think about it at minus 20 plus 100 R bar equal to 0, or at where R bar equal to 0.2. And once you plug that in here, you will get square root of 3 by 3. And if you do the approximation, this is almost equal to 0.58. And this is how it would look like pictorially. So this curve is this thing that we had here. That is what we drew. And this is the global mean variance portfolio, which is around 58% standard deviation. And these were the initial 3 assets. So this is one way in which you can actually derive this expression. Okay, so just one thing to note, that the analysis above assumed that the shorting of assets is allowed. And how do we know that? Because we actually just put in the restriction that the sum of the weights has to be equal to 1. So if shorting is not allowed, you have to put in one additional constraint, which is that all the weights have to be greater than or equal to 0, right? The rest of the problem is same. So you're still minimizing the same objective function, and you still have the same 2 constraints that we had seen before. But in addition, now there is an additional constraint. But the implication of adding this additional constraint, wi is greater than or equal to 0 for all I, is that now we will no longer get the nice result that we had, that the first order conditions are all going to be linear equations, right? So that is one complication. So this is coming from the fact that the objective function is quadratic as before. Constraints are linear equalities, which is also as before, but now some of the constraints are inequalities, right? So we cannot actually reduce the whole thing to a solution of set of linear equations. But the good news is this problem is still tractable in the sense that it can be solved numerically, right? So just qualitatively, one point to note here is that one difference between the case when short selling is allowed versus not allowed. So if short selling is allowed, most of the optimal weights that we are going to get are going to have non-zero values, right? So we'll end up essentially using almost all of the assets to construct our optimal kind of like minimum variance portfolios and so on, right? However, when short selling is not allowed, in that case, at the optimal point, so in the sense that the portfolio which minimizes the variance in this way we have been discussing, so that is going to often actually have a lot of assets having a weight equal to zero at that point, right? So this is just kind of like something to note while you are solving it.